So with eddy current testing, the theory of operation behind it is we've talked about this whole process is electromagnetic. We use a coil to produce electromagnetism. And that electromagnetism or that magnetic field, when we place that probe, which is going to create a magnetic field, when we put it near a metal part or a conductive part, that magnetic field is going to travel or go into that metal part. And the opposite, where we can use electricity to produce a magnetic field, but a magnetic field intersecting with metal is going to create a current. Right? And so at the points where that field is going into or intersecting the metal part, it's going to cause very small currents to flow through the part, little circular currents called eddy currents. And those are shown here in red. So the magnetic field induces a current flow in the material. These are eddy currents. What happens though is those eddy currents then are going to create a magnetic field of their own. Okay, so we've got the eddy currents will create a magnetic field, and that magnetic field is then going to go back and affect the coil. And it's going to create a change in impedance in the coil. This is how an inductive coil, when you put metal into it and take it out or move it, this is why the inductance changes in a coil that has a current running through it as you put it near metal, or if you put a piece of metal inside or outside of it. Okay. And so if we measure that, if we look at how much that affects the coil, then we can determine if there are changes in the amount of metal that's in front of the coil or near the coil. So the eddy currents produce a magnetic field. That magnetic field that they produce is opposite the one that the coil was producing. And that creates a opposed current in the coil. It's 90 degrees off. That's where that 90-degree offset comes from. That's part of inductive reactance. And so that causes the impedance shift that we see. And then we display that, we take that, we track it over time, and we put it on a display that we can see in order to perform the test. Now, the more sophisticated versions of these machines, the newer ones, will use multiple coils in what's called an array. And they can not only show that there's a change in the impedance, that can be run through a computer, and it can actually produce an image or a scan of what that metal looks like. Like it can show a 3D rendering of those changes in impedance, which gives you a 3D rendering of the part. Okay. So the way this is affected, we got a few things that happen with this. Those currents that occur, the eddy currents, when we get that magnetic field going in, and it's going to cause little circular currents to flow inside the part, they're going to be affected by the material that you are working with. Right? And what's called their density, how strong they become, is the current density, and that's how many of these little circular currents are concentrated in a given area. The current density ultimately is going to affect the accuracy of our test as well as the sensitivity and what kind of depth of penetration. How deep can we see? Can we see only just at the very surface, or can we see some things going on that are subsurface? That's going to be determined by this current density. Because remember, those eddy currents, not only are they there, they're creating a magnetic field of their own. And so if the stronger it gets, the more that magnetic field is going to affect our probe, the less it's going to be able to look further down into the part, for instance. So the current concentrates, it forms mainly at the surface and any material that's directly near the coil. So if you have a part that's not flat, it's not just going to be directly below the coil, it may be off to the sides to some extent. And so if you're moving your probe around the part and you're going from an open flat area, and you move your probe into an area where there's like another, a change in geometry of the part, that is also going to affect the output of that coil. So current density primarily is going to be at those surfaces, and then it's going to decrease exponentially as you work your way down into the material, as you move away from that surface. So what this causes is something called skin effect. That high current density at the surface, creating a high magnetic field, a stronger magnetic field at the surface, is going to, the stronger that is, the stronger that field forms, the more it's going to block the ability of the probe to, to be able to see down into the part. Okay. So that's where it can hide subsurface flaws. That's why this is primarily a surface, or if you're doing subsurface, it's on thin things like sheet metal looking for corrosion. And the most common is if you have a lap splice. You have two pieces of sheet metal that are on top of one another and they're riveted together. It's very common to get corrosion between them. And so you can pick that up with a eddy current tester. That's one of the labs you'll do, is look for corrosion between a lap splice. Okay. But you're not going to look through a big solid block, especially of a ferromagnetic material like steel or something like that. So that's going to affect, like I said, the depth of penetration. So the density of the eddy current is directly proportional to the penetration of the field. Okay. And the depth of penetration is it reduces exponentially as we go away from the surface. The strength of the eddy currents is going to reduce exponentially. And there's a point where we say, okay, it's no longer effectively, we're no longer effectively seeing into the part. And that point is where the current density has dropped to 37% of the surface density. Okay, where the strength of the magnetic field that's being caused by those eddy currents drops to 37% of what it is at the very surface of the part. And anything beyond that is below what's called the depth of penetration and is not going to provide an accurate signal or an accurate reading of what you might pick up. So below that, it's insufficient for testing. So, and these numbers are going to be calculated. This is not something as a someone who's just starting out or even performing eddy current testing at, say, an airline. You're not going to be figuring this out necessarily. Okay, there's 3 levels in non-destructive testing. In each method, you can be certified as a level 1, a level 2, or a level 3. And a level 1 is someone who performs the test and can basically get results. If there's interpretation required, you need somebody who's a level 2 that's had additional training and additional time performing the test. That's a level 2. And then finally, there's level 3, and level 3 are the people who design the tests. They decide what parameters, they decide what probes to use, what frequencies to set the tester at, what driver power to set it. And we'll talk about what those different things mean in a little bit. But someone who's a level 3 typically is like, they are like a test engineer. Oftentimes people that become a level 3, they have an engineering background rather than the technician background. Not to say you can't, not to say you can't go that route. But that's kind of a more common route for someone that's a level 3. If you really get into NDT, you want to make it a career, there's no reason you can't. You can't become a level 3. It just takes a lot of experience and a lot of time and a lot of a lot of attending kind of classes and learning how to do it, and then learning the math behind it and the theory behind it to be able to design those tests to be effective. So if we look at it visually, this is what we're talking about. So the depth of penetration, you can see here, kind of, you create these, the density, the flux density at the surface. You can see it has the most rings and spread out the widest. And it kind of creates this, this cone going down into the part where the strength drops off. And so the graph on the right shows you where that, at the very surface, we call it 100% power or 100% density. And then by the time you get down to, the 37% takes place at gamma there. And anything below that, yes, it will, the part will be magnetized. It will cause some eddy currents to form below that point, but it's not enough that it's considered accurate for testing below that. So in this part, you would only be able to effectively find flaws down to this level right here, roughly. And I can't draw a straight line if my life depended on it when I'm using a mouse. So imagine that's a straight line. Everyone's got imaginations, right? Hopefully be able to do that. If we look at a heat map of it, this is where you can see the eddy current coil up at the top with what they call a wear face, the thing that it slides along the surface. And then in this case, the part, it's showing the strength of those magnetic fields, okay? That's going on down inside. So it looks something like this. So really, in this case, you can see the eddy currents are forming to the left, to the right of the probe, as well as, ways below it. But really, the depth of penetration in the area that you're actually looking at right now is pretty much directly under. It's kind of the orange and red areas right there. That's about all you're seeing right now on the probe. Anything outside of that box I drew, you would have to slide, you would move the probe around, you have to slide around. And if you need to go any deeper than that, you probably have to go to a different method. You may have to use ultrasound, or you may have to use X-ray if you have to do something thicker. So what affects this? Where does our depth of penetration come in? So some of the things that can play a role in it. So the depth of penetration, this isn't the full equation, but rather, I didn't realize this was here the whole time. We'll get that out of the way. This is just a proportional equation. You can see the operating frequency is going to play a role. Okay, the frequency of the current that we're sending through the coil. The materials, what's called conductivity or resistivity. That's how well does the material conduct, right? We know some materials are better conductors than others. Plastic's a terrible conductor. Things like gold is a fairly good conductor. Copper's even better, but copper can also, you get like that patina on the outside of it, which can cause resistance to build up. So aluminum is going to have a different conductivity. So all your materials have different conductivities. Resistivity is the opposite of that, right? Conductivity, how well does it conduct? Or the better it conducts, the less resistive it is. That's why they're together. And then the last part, material magnetic permeability. How easily do magnetic fields form in the material? And different materials are more or less permeable, as we found out in magnetic particle. A hard steel, it's harder to form magnetic fields in it, so it's less permeable than a soft iron, where it's very easy to form magnetic fields. Okay. Aluminum is even less permeable than both of those. It's hard to form them, but when you're performing eddy current testing, there are magnetic fields forming in the aluminum. Or a bronze rod, when you run current through it, brass, bronze, or copper, you can run current through it and it'll create a magnetic field. But as soon as you shut the current off, it's going to go away. So the depth of penetration, you can see if the resistivity of a material is high, you'll get good depth of penetration, better depth of penetration. If it's low, your depth of penetration goes down. Those are directly related. Frequency, if you want to get a better depth of penetration, what would you do to frequency? Would you increase it or decrease it? What's that? You would decrease it. They're inversely proportional. It's under the thing, right? If you don't want to penetrate as deep, but you want to get better detail, or you want to get more fine, the ability to detect smaller items, what would you do? Well, I guess I'll ask you this. Can we do anything to change resistivity or permeability? No, those are properties of the material. So we got to understand those. But really the only thing that we can change in this equation, the depth of penetration, is the frequency, okay? So if we want to get deeper penetration, we have to go to a lower frequency. But when you go to a lower frequency, your resolution also goes down, okay? If you want very high sensitivity, you have to use high frequency. But what that means is you aren't going to be able to see as far into the part. Okay, your depth of penetration will get smaller. And so here's an example of that. So higher frequency, we get less penetration, but it's more sensitive. We're going to see a lot more near the surface. Okay, so when we're looking for those very fine surface cracks, say we're looking for fine surface cracks around like a rivet hole or a bolt hole, we're going to want to use a fairly high frequency. What about if we want to see corrosion? What do you think we would use? We would use a low frequency. Typically corrosion is going to be on the backside or inside the splice, the backside where we can access, if we have a splice, we can access the top or the outsides, but we want to look for corrosion between the metal. So if we're trying to see something further in the part or on the backside of a piece of sheet metal, then we're going to go to a lower frequency. We're going to lose some of that sensitivity, but we're going to be able to see further or deeper into the metal, into the material. Here's kind of a table of different materials. So we can't change resistivity and conductivity, but we have to understand that they're going to have an effect on this. So resistivity, conductivity are opposites. For a given frequency, you will get, if you have a high resistivity, you'll get greater penetration. If you have a low resistivity, you'll get less penetration. Okay. And you don't have to memorize, I'm not asking you to memorize it, I'm just showing you what some of these are. So for instance, most of what we're going to be working with is aluminum. And you can see the resistivity or the conductivity of aluminum is fairly high if you compare it to like bronze, a couple of things down. But if you go look at copper, you can see copper is significantly higher than the aluminum is, right? It's more conductive. It's a better conductor of electricity. That's why wire typically is copper, although you're seeing more aluminum wire because copper has gotten so expensive. The other part of that is permeability. And so permeability is how easily can we magnetize something, right? You can see they put air on here. Air is effectively 1. They start the scale with air. So you can, in theory, magnetize air. It's just 180,000 times harder to magnetize air than it is to magnetize soft iron, right? So the higher the number, the easier it is to magnetize something. You can see aluminum isn't much different than air. Aluminum doesn't like to be, it doesn't become magnetic, but it will create a magnetic field will form in it if you're running a current through it, or if you put it near a coil that has a current running through it. Whereas iron, you can actually get it will become magnetic. So high permeability, iron, for instance, less penetration. Why do you think that is? Why do we get low penetration with a material that magnetizes easily? What's going to happen? What is stopping? What causes that penetration to not occur? What? The magnetic field itself. So iron, where is that magnetic field going to form really strong? It's going to form right at the surface. It's really easy to magnetize. So it's going to form a really strong magnetic field right at that surface. So that's going to block our ability to see deeper into the iron. Okay. Where something like aluminum, that's not going to be nearly as strong as iron. Right. So we can see further in there. Low permeability then allows that greater, to see further. So some of these frequencies we commonly run, what will you have to set your thing at? Our testers can run from 50 to 50 hertz all the way up to 4 megahertz. Okay, 50 hertz. 50 hertz is kind of a voice range tone. Anyone heard a speaker ever buzz? No, that's a 60 hertz tone. Okay, this is a little bit lower than that. That buzz, that's 60 hertz, that's coming from your wall outlet. That's the AC in your house. If you hear that buzzing noise, that's 60 hertz. So this is a little bit lower than that. And I have terrible pitch, so I can't be up here and like, this is a 50 hertz. Not gonna happen. I don't know what that was. All the way up to 4 megahertz, okay, 4 million hertz. The typical range most of the time for aluminum is in the hundreds of kilohertz. Okay, so if we're working with aluminum parts, it might be, if we're trying to really get deep penetration, if we're looking for corrosion, it might be somewhere around 50 kilohertz. If we're looking for surface cracks, it's not uncommon to run our probes at 300, 400, 500, 600,000 or 600 kilohertz, right? 600,000 hertz. And you're deciding, because you can't control permeability, because you can't control conductivity, your frequency selection is where you're balancing that depth of penetration versus how sensitive your probes are going to be. But no, if you move from a material, if you're trying to say, okay, I know aluminum, I usually set up at a certain frequency, right? I set up at 400 kilohertz, for instance. And now I'm going to move to iron, and I know that iron is more permeable. What do you think you would have to do to see into iron to get a better, what do you typically have to do if you were to move to iron? Would you have to increase your frequency, or would we decrease our frequency to try to get that depth of penetration? We would decrease the frequency to offset the fact that the permeability has gone up, right? So that's why you kind of need to know that relationship. It's not so much like I'm going to design the specific test, but if I'm moving from one material to another, it's kind of that, does it make sense, right? I'm setting up my probe. I used it on this before. I know that aluminum's this, and now I'm doing something else. You can kind of use that to figure out, is my procedure correct? Am I doing something? Is it in the ballpark? Okay. If you get off readings, yeah, exactly. If all of a sudden things just aren't calibrating out like they should, and that maybe something happened to your tester. So you have that kind of check, like, reality check. Is my equipment working properly? Is the test written properly? Am I able to do what I need to do? Okay. The selection will vary with materials, and they're to balance differences in that: conductivity, resistivity, magnetic permeability. But we have to know too, what kind of a flaw are we looking for? Okay, usually when we're doing this, it's a no. Like, we're checking specific areas because we know a flaw is possible. We check around rivet holes because Aloha Airlines turned one of the airplanes into a convertible. And we know that cracking emanating from rivet holes is common. We have to check landing gear legs at the trunnion point, because every time the plane lands, the weight of the airplane is slamming on the trunnion. The trunnion's the big bolts that hold the landing gear in place, right? We have to check the compressor or the turbine case on the engine, because that gets hot and cold and hot and cold and hot and cold and hot and cold, and things that get hot and cold and hot and cold, they expand and contract and expand and contract, and they tend to crack. Okay. So we got a kind of an idea of is it a surface crack we're looking for, or are we looking for lap splice corrosion? Do we need to have deeper penetration into the bag? You got to keep that in place. In some cases, you can actually set testers up. Some of your newer testers, like, hey, I want to look for both surface cracks and corrosion. The tester can actually bounce between two modes. It can send a pulse. It can pulse for a minute at a high frequency and then a low frequency, and and it does this many times a second. So it's actually doing two tests at once, but you have to have a probe that's able to handle it. And that's where we'll go kind of in the next area. We'll start looking at the different types of probes and what they do. Some probes lend themselves more to high frequency, some to low. And then some of these real sophisticated ones, they might have more than one coil in the probe where it can do a high frequency, low frequency, low frequency, high frequency, low frequency. And so it can actually look for, you can get that high sensitivity at the surface, lower sensitivity, deeper penetration with the low frequency. So put that all together. So I'm going to leave off there.